Stand at a bus stop for a while, and two very different questions come to mind. Buses arrive, one after another, scattered along the passing minutes. The first question is, how long until the next bus arrives? That is a waiting time. It can be any positive number, so it is continuous. The second is, how many buses in the next hour? That is a count, a whole number, 0, 1, 2. So it is discrete. Two questions. But one thing drives them both. That one thing is the rate of arrivals. Lambda, a positive number telling you how many events happen per unit of time. Lambda is the heartbeat behind both questions. From that single rate grow to distributions, twins with the same parent. Which one you reach for depends only on what you're measuring. On the left, the exponential distribution. It models the waiting time between events, a continuous quantity. On the right, the Poisson distribution. It models the number of events inside a fixed window, a discrete count. Same lambda, two different roles. A continuous quantity gets a probability density function, a smooth curve. A discrete count gets a probability mass function, a set of bars. And running through both is the number E, roughly 2.718. Let's watch the process itself. Picture a single timeline, running left to right. Events land on it at random moments, but at a steady average rate lambda. There goes one, another. They arrive one at a time, and what happens in one stretch of time tells you nothing about a separate stretch. The intervals are independent. This is a Poisson process. Now look at the timeline two ways. Fence off a fixed window and count the dots inside it. The bus is in 1 hour. That count follows the Poisson distribution. Or measure the gap between two neighboring dots, the waiting time from one arrival to the next. That gap follows the exponential distribution. One timeline, both distributions living on it. Let's pin down the Poisson distribution. Let capital Y be the number of events in a fixed interval. The chance of seeing exactly k of them has one clean formula. The probability of exactly k events is e to the minus lambda times lambda to the power k, all over k factorial. That factorial is just 1 times 2 up to k, with 0 factorial defined as 1. And here is the fact worth carving in stone. For a Poisson variable, the mean and the variance are the same number. Both equal lambda. One more piece of bookkeeping. If events come at a rate r per unit time, and your window has length capital T, then lambda is simply r times t. Rate 5 per hour over half an hour gives lambda 2.5. Let's see the Poisson as a picture. Each bar is the probability of that many events. With lambda equal to 3, most of the weight piles up near 3, with a thin tail stretching right for the rare busy windows. The peak sits right around lambda, the mean. That is where the busy windows and the quiet ones balance out. Now watch what lambda does to the shape. Turn lambda down to 1, and the bars crowd against 0. Mostly quiet windows. Push lambda up to 5, and the whole mount slides right and spreads out, its peak marching along with lambda. Bigger rate, more events, further to the right. Now flip to the waiting time. Let capital X be the time until the next event. Because it can be any positive number, we describe it with a density curve. Its probability density function is lambda times e to the minus lambda x, for x at least 0. It starts high at lambda and decays smoothly towards 0. Long waits are possible, but less and less likely. The area under this curve is where probability lives. The chance you're still waiting after time x is the area out in the tail, and it works out beautifully clean. Shade the tail beyond x, and that area is exactly e to the minus lambda x. So the survival probability, the chance of waiting longer than x, is e to the minus lambda x. Its mirror image is the cumulative function. The chance you have waited at most x is 1 minus that. And the mean waiting time is 1 over lambda. The faster the events, the shorter you wait. The exponential hides a strange, almost magical property. Suppose you have already waited S minutes and no event has come. How much longer must you wait? The surprising answer? The past does not matter. This is called being memoryless. The remaining weight, given you have already waited S, is distributed exactly like a fresh weight from zero. The clock forgets how long you've been standing there. Here is the whole proof in 4 honest lines. A conditional probability is the joint over the given. And since waiting past S plus T already means you have passed S, the top is just the survival past S plus T. Substitute the survival formula on top and bottom. E to the minus lambda S plus T over e to the minus lambda S. The e to the minus lambda S cancels top and bottom, leaving e to the minus lambda T. And that is precisely the survival probability of a brand new weight. The dependence on S has vanished completely. Among all continuous distributions, only the exponential does this. Let's make it concrete. Buses arrive at an average rate of 4 per hour with exponential waiting times. So lambda is 4 per hour, and we will measure the wait x in hours. First rule of these problems: match the units. 15 minutes is a quarter of an hour, 10 minutes is 1/6, 5 minutes is 1/12. Part 1. What is the chance of waiting more than 15 minutes? We want the probability x exceeds 0.25 hours and survival is e to the minus lambda x. Plug in e to the minus 4 times a quarter, which is e to the minus 1. That comes to about 0.368, roughly a 37% chance of still waiting. Part 2 shows memorylessness earning its keep. Given 10 minutes already gone, the chance of at least 5 more is a conditional probability. But by memorylessness, it collapses to a plain wait of 1/12 of an hour. So it's just e to the minus 4 over 12, which is e to the minus 1/3, about 0.716. The 10 minutes you already spent make no difference at all. Now, a counting problem. A call center receives calls at an average rate of 6 per hour, and arrivals follow a Poisson model. The key first step is always to find lambda for the window in question. For 30 minutes, lambda is 6 times a half, which is 3. For 10 minutes, lambda is 6 times 1/6, which is 1. Two windows, two different lambdas. Part 1. The chance of exactly 3 calls in 30 minutes. Here y is Poisson with lambda 3. So the probability is e to the minus 3 times 3 cubed over 3 factorial. 3 cubed is 27. 3 factorial is 6. And 27 over 6 is 4.5. So it is e to the minus 3 times 4.5, which is about 0.224. Part 2. The chance of at least one call in 10 minutes, where z is Poisson with lambda 1. At least one is easiest through its complement. 1 minus the chance of 0 calls. The chance of 0 is e to the minus 1 times 1 to the 0 over 0 factorial. That is just e to the minus 1, about 0.368. So at least one call is 1 minus that, roughly 0.632. A little over 60%, the busy window is more likely than not to ring. Your turn. A shop receives customers at a rate of 2 per hour with exponential waiting times. Pause the video and work out two things: the mean waiting time and the chance of waiting more than 1 hour. I'll wait. Here's the walkthrough. The mean wait is 1 over lambda, 1 over 2 of an hour, which is 30 minutes. On average, a customer every half hour. For the tail probability, survival is e to the minus lambda x. So waiting more than 1 hour is e to the minus 2 times 1. That is e to the minus 2, about 0.135. So there is only a 14% chance of waiting beyond an hour. If you got both, you have genuinely got this. Trap 1. And the deadliest, swapping the mean and variance. For the exponential, the mean is 1 over lambda, and the variance 1 over lambda squared. For the Poisson, both are simply lambda. Keep the two families apart. Trap 2. Forgetting to rescale lambda. If the rate is per hour but the window is 10 minutes, You must multiply rate by the interval in hours first. A mismatched lambda quietly ruins everything downstream. Trap 3. Confusing the two questions. How long until the next event is exponential? How many events in a window is Poisson? Read which one the problem is actually asking. And trap 4. Small slips. Only the exponential is memoryless. Do not apply that shortcut anywhere else. And in the Poisson formula, get your factorials and powers exactly right. 0 factorial is 1, not 0. Let's lock it all in. The exponential governs the waiting time between events. Its density is lambda e to the minus lambda x. Its survival is e to the minus lambda x. Its mean is 1 over lambda. And it alone is memoryless. The Poisson governs the count of events in a window. Its mass function has that e to the minus lambda, lambda to the k over k factorial, and both its mean and variance equal lambda, with lambda equal to rate times interval. Same lambda, two roles. Exponential for the times between events, Poisson for the counts within them. Recognize which the problem is asking, reach for the right formula, and this whole family of arrival and counting problems falls open.